So in today's lecture, I'm going to be talking about population dynamics. This is a useful starting point to understand all kinds of ecological problems. In real ecology, one has populations that are spread in an environment. Here, I'm talking about a much simpler situation where I'm just thinking about a zero-dimensional system. And the only degree of freedom is the number of reactants or the number of species or the number of individuals in the system that are evolving by some kind of simple process. So I'm going to be talking about the two simplest population dynamics processes, pure birth and birth and death. And even though these processes seem so simple that you would imagine everything is known about them, and yes, everything is known about them, they're still very rich. They have interesting phenomenology, and also it illustrates a number of mathematical tools, again, to solve these systems. And so the generating function will again play a prominent role in this. And so I hope that by seeing it yet again, you get more familiar with it, you get less intimidated with how you deal with these sorts of master equations. So the first example is pure birth. So in a pure birth process, you can imagine bacteria, and bacteria divide. And so if I have a bacterium of type A, then a little later on, it turns into 2A. And so that's all there is to it. And what we want to ask is, what is the population as a function of time? What is the probability distribution of the population at a given time? So if we want to write, so let me call n will be defined as the number of individuals. I'll use that throughout the lecture. Individuals. And so the rate equation is trivial. N dot, how does n change? Well, everybody gives birth at the same rate. So I imagine here that this process occurs at the rate 1. So everybody's giving birth at rate 1. And so n dot just changes as n, because everybody gives birth at rate 1. There's n of these guys, so the total birth rate is n. And if I begin with the monomer-only initial condition, and that's always what I'm going to start with. So here I'd start with just a single bacterium. Then the solution to this is n of t. Okay, so the rate equation is just this. We have just exponential growth. And then we can also look at the probability distribution for the number of particles n. And so let me write down the master equation. So the master equation, so again, let me define P sub n will be the probability that there are n particles in the system. So P sub n is the probability that there is n particles at time t. So this is Pn of t. So the master equation is nothing more than, well, Pn, how can that change? You could have n minus 1 particles and one of them gives birth, and then you increase the probability that there are n particles in the system. So you have n minus 1 particles that each give birth at rate 1, and so you have a gain term, n minus 1, Pn minus 1. And there's a corresponding loss term, because if I have n particles in the system and one gives birth, then I lose a probability of having n particles in the system, and it happens at this rate. So this is what we're going to concentrate on for the next while, just to solve this equation in complete detail. But before I do that, let me do a number of preliminaries, just because this is a good pedagogical point, which is if you stare at this equation, you might see that it kind of looks like, so let me just recall now, the Poisson process. So the equation of motion in the Poisson process, if I call Pn, again, the probability that there are n particles in the system, in the Poisson process, what's happening is that you go from n to n minus n plus 1, n plus 2 at a constant rate. So the Poisson process equation is Pn dot is equal to Pn minus 1 minus Pn. So you see that they kind of look morally similar. And in fact, well, we'll see like how similar or how different they actually are. Now for the Poisson process, let me just remind you what the solution is. Pn of t is equal to t to the n over n factorial e to the minus t. And in fact, that's not a terribly useful form of the solution, even though it's exact, because you have a factorial, so you don't see the analytic structure. But in the limit of large time, t go to infinity, this just goes to a Gaussian, a translating Gaussian, e to the minus n minus t squared divided by 2t divided by the square root of 2 pi t. And if you've not done that exercise, I highly recommend that you do it. Now, why did I spend some time on this? Because you see that for this equation, the solution has a simple scaling form. And so we know that the distribution is translating to the right at a rate t, and the fluctuations about the average number of particles is small. So now I return to this system of equations and ask the same question. What is the average position of n, which we know already is growing exponentially, and what are the fluctuations about the average position? Are they small? Are they fixed? Are they large? And so the new feature about the pure birth process is, even though this process looks very similar to the Poisson process, it has very different character because the fluctuations are huge. And in fact, the distribution has nothing in common with the Poisson process. It's not a scaling distribution. Well, it is a scaling distribution, but it has weird features associated with it. So that's what I want to turn to now, which is let's now look at the fluctuations associated with this master equation. So again, before we actually go into the details of solving the master equation, let's suppose that we were intimidated by this equation and said, well, let's look at the average values. Maybe we'll look at the mean and the mean square and see like what kind of insight we can get from that. So let me do that next. So let's look at moments. And so let me define the mth moment, m to the k, will just be defined as summation n to the k. Actually, where will I put this? Let me put it down here, mk, n to the k pn. N equals 1 to infinity. So that's the kth moment of the distribution. So let's now look at the moments one by one. So the first natural moment is the first moment, m1, which is nothing more than summation m1, which is nothing more than n pn. So let's ask how this evolves with time. So we can take the time derivative, so it's m1 dot is n. There's no 1 here. There's just n pn dot. And so we just have summation over all n from 1 to infinity, 1 to infinity. And so we have n, and then pn dot. So that's equal to n minus 1 p n minus 1 minus n pn. And now it's kind of pleasant gymnastics to play around with these infinite sums. But you see here we have a pn minus 1, and here we have a pn, and somehow we'd like to cancel a lot of terms. And the way to do that is to redefine the variable in the first summation. Instead of using n, let's call that m, which is n minus 1. So I have the same index for the two terms. And so the first term becomes the summation. So if I say that n minus 1 is m, it becomes n plus 1 times n pn. And the summation, if n goes from 1 to infinity, m goes from 0 to infinity, but 0, the term of 0 is 0, so we can still make it 1 to infinity. We have minus summation n pn. So what I did in going from this line to this line, I said, let's replace n minus 1 by m. And since we're all friends here now, and it's a dummy index we're summing over, I said, well, let's call m equal n. And so all you do is just shift the indices. What? Squared. Thank you. Okay. The first term, what? Yeah, the 0 term doesn't matter because it has coefficient 0. Okay. And so now we're in a position to cancel the quadratic term. N squared cancels this n squared, and we just have summation n pn, which is nothing more than m0. So m1. So we just recover our original rate equation that m1 dot is equal to m1, and so m1 just grows exponentially with time. Slightly more interesting, in fact, much more interesting, is let's look at the second moment. So m2 dot. So summation n squared pn. So that's equal to the summation. So we have n squared n minus 1 Pn minus 1 minus n squared n cubed Pn. And again, I do the same index shifting game. And you know, once you're used to it, it's like it comes second hand. But you know, the first few times you have to do it maybe pedantically, step by step. But this is just, again, n plus 1 squared n Pn minus n cubed Pn. And so the cubic terms cancel, and now I have 2n squared plus n Pn summation. And so this is nothing more than 2m2 plus m1. And so this is m2 dot. We know what m1 is. It's just e to the t. And now we just solve this by, like, you know, sophomore differential equations. So I can write this as m2 dot minus 2m2 is equal to e to the t. And then I see, well, I put this in a form to use an integrating factor. The left-hand side is nothing more than m2 e to the minus 2t dot. So I multiply this equation through by e to the minus 2t. And then this is nothing more than just this. And here I have equals e to the minus t. And so I integrate this equation, and I get m2 e to the minus 2t minus m2 e to the minus 2t at t equals 0. This is 1, and this is 1. So m2 e to the minus 2t minus 1 is equal to, and then I have to integrate e to the minus t. And so that's 1 minus e to the minus t. So finally, m2 is equal to 2 e to the 2t minus e to the t. And the factor 2 here turns out to be important because a natural thing that you might want to measure is the variance of the distribution, which is nothing more than m2 minus m1 squared. And m2 minus m1 squared, so I just subtract away e to the minus 2t, and I get e to the 2t minus e to the t. So the variance divided by m1 squared is of the order of 1. Which means that this system has huge fluctuations. Which means that looking at the moments is actually useless because it misleads you, because you think, well, the first moment, the average number of particles is growing like e to the t, but it tells you nothing about the actual distribution. Whereas in the Poisson process, if you know the average number in the Poisson process, then you know the distribution is tightly peaked about that average number, and you have a good sense of what the system looks like. So now we have to actually bring out the heavy artillery and solve the master equation directly. So that's our next step. So to solve the master equation, how am I going to do it? Well, I'm going to show you 2 techniques for solving it. First, I'll do it the conventional way by the generating function technique. And then I'll show you a much sleazier and slicker and simpler way of solving the same set of equations, which when it works like a charm, but when it doesn't work, it falls flat on its face. But it's nice to know that this method exists because it's like something you should try first before you bring out the heavy artillery. So we're going to try the generating function solution now. And I'm going to do this pedantically and step by step because, I would like you to feel like you see every step and, oh yeah, I think I can do this myself because, at some point you have to do this kind of stuff yourself. So I'm going to define f of z is equal to the summation from n equals 1 to infinity, Pn of t, z to the power n. So in principle, this is a function of, I should put here the time argument. So this generating function depends on time. Okay, so let's take our original master equation and do the same trick we've done many times before, which is multiply by z to the n and sum up and try and write it in terms of the generating function. So we have Pn dot is equal to n minus 1 Pn minus 1 minus nPn. I multiply by z to the power n, and I sum from 1 to infinity. So on the left-hand side, we just have f dot. And in fact, let me be a little bit careful here, because since there's two arguments, it really should be partial derivatives. So let me write this as df by dt. Okay, so now we have n minus 1, Pn minus 1, z to the power n. What do we do with it? Let me maybe do a little worksheet over here, because it's just a little bit of busy work. And so we have something that looks like 1 to infinity, n minus 1, Pn minus 1, z to the power n. And you see that there's an n minus 1 in front, which somehow ought to be generated by doing a derivative. So let's do that. Let's first of all write this as z, and then I have summation 1 to infinity, n minus 1, Pn minus 1, z to the power n minus 1. But now I can write this thing as just nothing more than z d by dz of the generating function. I can write this as z, and then there's z d by dz of summation n minus 1, Pn minus 1, z to the power n minus 1. But this sum is exactly the generating function. The term n equals 1 doesn't contribute, so it's just the generating function. So it's just z squared d by dz f. So the first term is equal to z squared times df by dz. And it should not come as any surprise that the second term is just z df by dz. So we transformed the set of master equations into a single first-order linear partial differential equation. In fact, this is nothing more than the wave equation. And it shouldn't be a surprise that we should get the wave equation out. Yes? Did I do something wrong? Yeah, but I multiplied back by z. Let me go back a step. Okay, so this step we agree, I didn't do anything. And in this guy, if I differentiate this one, I'm sorry, I see what I did wrong. That's what I did wrong. Okay, so this is Pn minus 1, z to the power n minus 1. So when I differentiate this, down comes an n minus 1, I have z to the n minus 2, but this z restores it back to it. So thank you for keeping me honest. Okay, so anyways, this is a wave equation, and I wanted to say here is that it shouldn't be that much of a surprise, because if you go back to even the Poisson process, if you were to expand this in a Taylor series, you'd get Pn dot is dp by dn, which is just the wave equation. You do the same thing here, Pn dot, and expand this in a Taylor series, and it's like the combination n Pn d by dn is that sum equals 0, and so it's a wave equation. But here we see it explicitly in doing this generating function. And let me also mention that when you're dealing with these sorts of stochastic processes which involve hopping on a one-dimensional line, whether it's a random walk or a population biology model, whenever you do this generating function, you'll always get to the form of a wave equation. And so standard techniques to solve it. Okay, so how do we solve this wave equation? The trick here is to write this as df by dy. And here, the new variable y is defined by dy is equal to dz divided by z times z minus 1. So once we do that, we basically have solved the problem. So our equation that we have then is, and now I'm being lazy, let me call subscript for differentiation. So I have ft is equal to fy, and the solution is f, which is a function of, well, so, here, by transforming from z to y, my generating function is a function of y and t. This is now any function, g, of y plus t. So g is arbitrary. And the way that we fix this arbitrary function will be by the initial condition. So that'll be the key. And you know, in general, when you have a wave equation, once you define the initial condition, then you find the solution for all time. So to make progress, we're going to have to first solve for the relation between y and z, and then we have to express the initial condition in the right way, and then we're in business. So let me do those two steps in turn. So first of all, let's solve for y as a function of z. So here we have dy. And you know, typically you have like a low order polynomial here that you resolve by partial fraction decomposition. So dy is equal to dz. And then I can write this as so there's a z minus 1 here and a z here. I guess I want a minus sign. 1. And this, well, this is nothing more than the differential of log of z minus 1. This is differential of log of z. So this thing is nothing more than d log of z minus 1 over z. So y is equal to log of 1 minus 1 over z. E to the y is equal to 1 minus 1 over z. So I apologize that this is a little bit too step-by-step, but I think it's helpful at this stage of familiarity. So e to the y is this. And then I have z is equal to 1 divided by e to the y minus 1. So this is how I'll go back and forth between my two variables. Okay, so we're almost done. Now we have to say, well, so we fix. So this is step 1, was compute. Did I make a mistake? Did I make a mistake? Backwards. 1 minus e to the y. That doesn't record with my memory, so let me just make sure that it is right. It is right. Okay. Okay, so step 1 was relate y and z, and 2 is we have to fix g. So how do we fix g? We say, well, at the initial condition, f, y, t equals 0. What is the initial generating function? So if we start with a single particle, then the initial generating function is equal to z. But this is wrong in the sense that it's the wrong variable, because in order to have solved our wave equation, we went to the y variable. So we have to re-express z as a function of y. So this is nothing more than 1 divided by 1 minus e to the y. So now we have the initial condition in terms of the right variable. And now the general solution, f of yt, well, f of yt is some function of y plus t. So t equals 0, here is our function. So to get it for general t, it's just equal to 1 divided by 1 minus e to the y plus t. So that is my general solution. That is the solution. And now what we need to do to make progress or to finish the problem is that we now want to expand this in a power series to extract the nth term in the series and thereby compute the number of particles and the probability distribution for the number of particles. So how do we do this? So again, now that we have the correct solution in terms of y, what we want is we want to write it in terms of z and then do a power series expansion in z. So now we go back to writing it as a function of z. So now we'll write f of z t is equal to 1 divided by 1 minus e to the, well, e to the y, I have it over there. So it's minus 1 minus 1 over z times e to the t. And now let me just manipulate it a little bit to make it into a form that I can expand it in a power series. So let me multiply through by z. Let me also multiply through by e to the minus t. So z e to the minus t in the numerator. Down here I'll have z e to the minus t minus z minus 1. And I'll write this as z e to the minus t. And I have 1 minus z 1 minus e to the minus t. And now this is easily expandable in a power series. So this is equal to z e to the minus t, and then I have summation from n equals 0 to infinity, 1 to infinity, sorry. 1 to infinity, and then I have e to the I have z to the power n, 1 minus e to the minus t to the power n. You know, just power series expansion for small z. And then from this, we can read off immediately what Pn of t is, because it's just the coefficient in z to the power n. So it's the coefficient of z to the power n, because there's one power of z here, it's the coefficient of n minus 1 in this guy. So finally, Pn of t is equal to e to the minus t, 1 minus e to the minus t to the power n minus 1. So that's the final result. Questions? What? What? No, it shouldn't start from 0 because, oh, here. Oh, thanks. Fine. Thank you. Pardon me? Well, the point is that the generating function was, where did I first write it? It was here. So it's a power series representation. And so here you should think of this as z is small and you're expanding in a power series in z, and we want the nth term. So once we have the full form, in order to like identify the terms in the power series, you again have to expand it for small z. So it's the same as, I don't know if you were at the tutorial 2 nights ago where I solved the Fibonacci sequence by the generating function technique. It's always the same kind of thing, that when you have a power, when you have a generating function, what you want are the coefficients in the power series. So you're doing a power series about z equals 0. Any other questions? Why is what? You're saying going from here to here? No, this is 1 minus az, and so I expanded power series 1 plus az squared plus az cubed. It's just binomial expansion. Maybe this should be a little bit bigger here. Have I made a mistake? Okay. Okay. So this is the answer. There's a couple of amazing things about, you have a question, yeah. Here. Because, the equation is the wave equation, and the solution to the wave equation is any arbitrary function of y plus t. Boy, this is getting a lot of buzz. Anyways, let's look at this, because it's, first of all, let me maybe look at the scaling form of this. So in the asymptotic limit, this is e to the minus t. And then when t is large, I can write this, I have 1 minus a small thing to the nth power, which is exponential of this thing. So this is nothing more than e to the minus n, e to the minus t. So kind of a funky looking object, but that's what it looks like. That's a scaling, the asymptotic form of this thing. But the point about this, which is really worth emphasizing, is if I look at this probability distribution, so here's a function of n, here is Pn. What is the most probable value of the distribution? The most probable value is my bacterium is lazy and says, I'm just not going to divide. And if he doesn't divide, you have a value here at n equals 1, which is e to the minus t. The next most probable thing is that the bacterium divides once, and then the 2 daughter cells say, we're going to be lazy and not do anything. And so for 2, it's down here. For 3, it's this. So it's an exponential distribution, but it's just that the support of the distribution goes all the way out to Antarctica, way the hell out there. And so the most, even though, so what I would say here is that n most probable is equal to 1. That's the most probable value of n. But n average is equal to e to the t. So the most probable value and the average value have nothing to do with each other. So it's like in a sort of hypothetical class of a billion students, most everybody is a dummy, but there's one Ramanujan who's just like brings up the average to being exponentially large. So that's what happens in the pure birth process. So I went through this like really step by step because I want you to try and feel comfortable with this methodology. So when you see these sorts of equations again, you'll have some sense like how you might go about dealing with them. So any questions with this? Yes? Because I'm starting with one particle in the system initially, so my initial generating function, so at t equals 0, I have Pn of t, I should have written this out perhaps, is equal to delta n0. I have just one, I'm sorry, delta n1. I just have one particle in the system, so the probability is non-zero only when n is equal to 1. So I plug this into here, then I get that the initial generating function is just equal to z. Other questions? Okay. Before I go on to anything more complicated, I want to show you a really slick trick that you can use to solve this type of equation. And if you think back when you were first exposed to differential equations, you know, and you learned about things like constant coefficient linear differential equations. What is the solution to a constant coefficient linear differential equation? And you learn that it's exponential. So when you're confronted with a constant coefficient differential equation, you assume an exponential, plug it in, and find some self-consistency. So similarly here, it turns out that for a lot of the types of problems that we're going to be dealing with, or that you do find in non-equilibrium statistical physics, the solution is an almost exponential solution. Notice that without this e to the minus t, you know, this is like, you know, some constant coefficient times n minus 1, where it's an n here. So it's kind of like almost, but not quite an exponential. So what you can do to like bypass a lot of pain is that you just say, well, when I'm confronted with these sorts of linear, random walkie type differential equations, maybe it's worth trying an almost exponential solution from the outset. Let's try it, and let's see what happens. And as you'll see, that it makes life, it simplifies the algebra considerably. So, alternatively, let's try Pn of t is equal to capital A, little a to the power n, where both big A and little a are time dependent. We know this has to work because as you see our solution has this form. But the point is, just as when you are confronted with constant coefficient linear differential equation, you say, let's assume exponential solution. So I'm saying, well, let's assume this because we kind of, you know, it's, if you don't know this, if you aren't exposed to this at the beginning, it seems like this is a magical guess. But once you see that we saw in constant kernel aggregation, the solution was almost exponential. Remember, it was 1 over 1 plus t squared, t over t plus 1 to the power n minus 1 for the concentration of clusters of size n. In other problems, there's the same kind of almost exponential character. So once you see it 4 or 5 times, then you say, well, maybe I should be smarter about how I think about solving the problem, and let's try this right from the outset. So let's try this and see what happens. So yeah, so then let's then compute Pn dot. So Pn dot, so we just have to differentiate this. So this is going to be equal to A dot times A to the n minus 1 plus n minus 1 A to the n minus 2. Now, because I know what the answer is and how to deal with this, I'm going to do a little bit of sleight of hand here, which I'm doing nothing, but it just reshapes this into a way that's convenient for later consideration. So I'm going to write this as 8. Thank you. A dot. So I'm going to do the following little thing here. Is I'm going to divide this guy by A, and then I have capital A to the n minus 1, which should be common factor outside. And over here, I'll write this as n minus 1 a to the, and then what I'll do here is I'll write this as n minus 1 over a dot. And then there's a common factor, capital A to the n minus 1. So that just turns out to be convenient. So now let's what happens to the master equation. So the master equation now becomes the following thing. So on the left-hand side, we have this capital A, little a to the n minus 1, and then we have capital A dot over A plus n minus 1, little a dot over little a. And on the right-hand side, we have n minus 1 Pn minus 1. So that is n minus 1, and Pn minus 1 is capital A, little a to the n minus 2. And then I have minus n Pn, so that's n a, little a to the n minus 1. And what I'm going to do now is that I'm going to separately equate terms of order n minus 1 and terms of order n minus 1 to the power 0. That's why I kind of did this regathering of terms here. Because those two sets of terms are linearly independent. So here I'll write this as n minus 1. Then I have big A to the n minus 2, minus big A to the n minus 1. And then I have the leftover term, because here what I did is I wrote this is minus n minus 1 minus plus 1. And so there's another term here, minus A to the n minus 1. So now we separately equate coefficients of n minus 1 to the power alpha. So the term n minus 1 to the power 0, so let's look for terms n minus 1 to the power 0. What? I am being, oh, here. Thank you. Yes, I can't copy from one line to the next. Thank you. Okay, anyway, so n minus 1 to the power 0. So let's see. So here we have, there's a to the n minus 1. There's a dot over a. So on the left-hand side, we're going to have a dot times a to the n minus 1. And on the right-hand side, we have equals minus a to the n minus 1. So this goes away, and we just have a dot is equal to minus a. Even I can solve this equation without any work, and it's just a is equal to e to the minus t. The power n minus 1 to the power 1. So let's see what's within here. So what we have is a, little a to the n minus 2, a dot is equal to, and over here we have a to the n minus 2, 1 minus a. And so the a's cancel, the a's to the n minus 2 cancel, and I just have a, little a dot is equal to 1 minus a. And even I can solve this equation, a is equal to 1 minus e to the minus t. And then we get our answer. So when this works, it works like a charm. And I just want to point it out because it's a really cool technique. And in fact, we're not quite as smart as we could have been because we know that the probability distribution better be normalized. The sum Pn has to add up to 1 because the probability that there's any number of particles in the system has to be 1. So in fact, big A and little a are not independent. So in fact, by using normalization, you could just have a single equation to solve and you'd have even less work. And then for some of you might be saying, like, how did I know to put the n minus 1? Why didn't I like separate terms and powers of n and 1? Well, you could have done that. You could have separated powers of n and powers that are order 1, and you would find after 2 more steps, you get to the same result. So I just, it's one of these things that once you're used to playing with this, you try and take every shortcut you possibly can take. So any questions with this example? Yes? What was the what? Because you know, we have some equation, and there's powers of, you know, powers of n to the 0, n to the 1, n to the 2. These are linearly independent coefficients, and if they're going to be equal, each coefficient has to be equated. So again, well, okay. I guess there's not anything more to say about that. It's just that it's linear independence. Well, I guess this is a good example because I feel there's a lot of buzz in the room, and you know, it's just, this I think exemplifies a lot of the techniques that are like the bread and butter of non-equilibrium stat nav. Yeah. Except for the fact that in many classes of problems like this, the solution is of this form, almost exponential. And that's why I tried it from the outset. Right. Well, no, the thing is that if you assumed an exponential, you said, let me try big A, little a to the power n, something would be messed up, and you'd see like something isn't quite matching, and then then you have to try n minus 1. Yeah, the exponential solution doesn't work because it isn't the solution to the problem. Okay, so that was the birth reaction. Now let me turn to something which is a little bit more realistic biologically, which is birth and death. So now I'm going to have birth, death. So what I have in mind now is that bacteria can reproduce, and they reproduce, say, at a rate lambda. But bacteria also die, so A goes to 0 with the rate mu. And let's again kind of be naive about what we might expect to happen, and then let's solve the master equation and see what happens when we really solve it exactly. So again, we could write a rate equation for this process. So how does the number of individuals change as a function of time? So if everybody gives birth with the rate lambda, the rate at which the population increases will be nothing more than lambda times n. But everybody dies at a rate mu, and so the rate at which particles disappear is nothing more than mu n. So this equation has 3 solutions depending on the relative size of lambda and mu. So n of t does the following thing. It's equal to e to the lambda minus mu t if lambda is bigger than mu. So if birth wins out over death, it goes like e to the minus lambda minus mu t if birth loses to death, and so the population will clearly go extinct in a time scale of order log of the initial number of particles. If the initial number is 1, it's like time of order 1. And here it's static for lambda equals mu. And so the question is, well, what happens in reality? And in some sense, the biologically interesting case is the static case, because if lambda is less than mu, then the population goes extinct right away. There's nothing to talk about. If lambda is bigger than mu, then whatever bacterium that it is will take over the entire planet. We'd be wiped out, and there's nothing to discuss because we just have a planet full of bacteria. So the interesting case is lambda equals mu. That's the physically relevant case. So we're going to, again, apply the generating function technique to solve this problem. And as we're going to see, everything is essentially line by line is identical. It's just mathematically more messy. So at some point, I'm going to outline the solution, and then I'm going to say, you guys do all the horrible steps in between, and I'll just write out the solution, and then we'll examine what some properties of the solution. Yes? Oh, I'm sorry. Sorry. My mistake. Okay. So, once again, let's write down the equation for the master equation for the probability distribution, Pn dot. So, it's going to be equal to lambda n minus 1 Pn minus 1 plus mu n plus 1 Pn plus 1. And then I'll have minus lambda plus mu n Pn. So that's what we want to solve. By the way, let me just also mention another kind of amusing observation about this. Let's for the moment consider the case lambda equals mu. So then we have, it looks kind of like a random walk master equation, except the rate at which you hop is proportional to how far away you are from the, actually, I didn't say that correctly. No, I guess I did say correct. Yeah, the rate at which you hop is proportional to how far away you are from the origin. So we can think of this in the case, let's talk specifically about the case lambda equals mu. So we can think of it as a random walk in n space. And as we get further and further away from the absorbing boundary, we're hopping faster and faster and faster. We know that for the pure random walk, that it is guaranteed to come back to the origin, that the random walk, if we imagine that at the origin is an absorbing boundary, the random walk is sure to be extinct. Here we have a different type of random walk process. It's hopping faster and faster as we're moving further away. So question, does this system go extinct when lambda is equal to mu? According to the rate equation, it says the system is static, and if it's static, that means that nothing is absorbed, and so it seems like it should live forever. But is that really the case? So you can ponder that as we actually solve for the probability distribution and see what comes out. So, and by the way, if you want even more fun things to think about, you can ask, well, what happens if you have a nonlinear process where instead of having linear in n, it's some arbitrary power event? This has not been solved yet. So if anyone knows how to solve this master equation with nonlinear powers of n, more power to you, and you can write a famous paper. Anyways, let's now solve this thing by the generating function technique. So again, I'll define the generating function. And so we're going to have, we take this set of equations and we multiply by z to the power n, and we sum from, and now the only difference is we should sum from 0 to infinity, because the generating function should also include the possibility that you go extinct. So in distinction to the case of pure birth, where if you start with one particle and the system is only giving birth, there's no way of having 0 particles. Here I should include the 0 term. So that's why the summation goes to 0. And so we end up with df by dt. And so maybe I should do a little worksheet on the right to, we already know what happens with these terms, because we already did them in the case of the birth process. So for n minus 1, so this is going to be lambda z squared df by dz. That's this term. For this term, we're going to have minus lambda plus mu z dp df by dz. Can anybody guess what this term is going to be? Plus mu. I mean, you can do it out, if you do a little worksheet, but I mean, you don't have to do very much, because this was quadratic, this was linear, this is power 0. So it's mu df by dz. So once again, we have a wave-like equation, because we have this polynomial lambda z squared minus lambda plus mu z plus mu, all of this multiplying df by dz. And so we have a wave equation again, because all we have to do is then write this as df by dy. And then we know what the solution is. It's an arbitrary function of g of y plus t. So all we need to do to solve this explicitly is we have to just invert this relation. We have to compute y, which is nothing given by dy, is equal to dz divided by lambda z squared minus lambda plus mu z plus mu. So I'm getting close to the end of where I'm going to do step by step, because at some point it just gets messy. But let me do a few more steps here. Question? Okay, you're happy? Okay. So this is dz. First thing is that this is a quadratic polynomial, so we could factorize it. Just here we had a quadratic polynomial that was trivial to factorize, but this is still factorizable. And so this is what? Lambda z minus mu z minus 1, which I'll write as dz. And then I'll factor out a lambda. So it's going to be z minus z1, z minus z2, where z1 is equal to mu over lambda, and z2 is equal to 1. And now I'm almost in business because I can write this as equals dz divided by lambda, and then I'll write it as z minus z1, z minus z2. And so then it would be 1, 1 minus, and then there is 1 over z1 minus z2. And so finally, I have dz, and lambda is, so z1 is mu over lambda. So when I multiply through here, I'm going to get mu minus lambda. And then here I have 1 over z minus z1, z minus z2. I'm starting to get tired here, so I'm going to, at some point, I'm going to give up, and I'll tell you what the answer is. But let me just do like a couple more steps. So this is nothing more than d of logarithm of z minus z1, z minus z2 to the power 1 over mu minus lambda. So that's what y is. And so z minus z1, z minus z2, z minus z2 is equal to e to the y, e to the mu minus lambda y. So anyways, now we do just what we did over here, is that the initial condition, f of y t equals 0, well, that was equal to, so now for the case of starting with a single particle initially in the system, my generating function initially is just z. But z, I shouldn't write it that way. I should write it as a function of y. And so this is, so I've got to solve, okay, now I'm giving up. So I've got to solve for z as a function of y. So I'll write it there. And then I have that, and then I can get my generating function from there. So I'm going to stop because this is just, it gets a little bit tedious. And let me just quote for you the answers, because the answers are interesting. So after 7 more steps, and I'm guessing that it's 7, but maybe it's 8. So we have Pn is equal to, so let me call it script capital E, and I'll define everything in just a moment, 1 minus mu over lambda squared, script capital E minus mu over lambda squared times little a to the power n minus 1, almost exponential solution. And P0, the only one which is unique is P0, and that's equal to script capital E minus 1 over a lambda minus lambda over mu script capital E minus 1. Where in this formula, I have to define script capital E and A. So script capital E is the exponential growth factor, e to the lambda minus mu t. And little a is equal to script capital E minus 1 over script capital E minus mu over lambda. So this form is not terribly revealing because, you know, everything is sort of implicit and you have to play around with it a bit. But first point to emphasize is that the solution has almost exponential character. So another way you could have solved this with less heavy artillery is by assuming an almost exponential solution and trying it out. But now let's try and turn to some physics. Let's try and extract some physics out of this formula. And perhaps the most interesting thing to ask is, in the limit where lambda and mu are the same, what happens? Does a population go extinct? Does a population live forever? What? Okay. Did anyone have any guess? So when lambda equals mu, birth rate equals death rate, does the population go extinct or does it live forever? There's no net bias. It's a random walk on a semi-infinite interval, but with this weird hopping rates. Goes extinct. Why? Why? But yeah, it's like must. Yeah, that sounds pretty reasonable. Why? So you say it might come to zero, and if it comes to zero, then obviously it's dead. But might it not come to zero? What? Yeah? Well, okay, so when lambda is equal to mu, you see there's some weird things going on here, because when lambda is equal to mu, this is 1. So this becomes 1 minus 1, which is 0, but it's 0 over 0. So it's a little bit ambiguous. So let's now look at this and actually find out what the answer is. Well, actually, there's no phase transition, because there's only two possibilities. Either you never hit the origin, or you hit it infinitely often. And so, you know, yeah. Yeah. Yeah, well, so let me now tell you part of what the answer is. When lambda is bigger than mu, when the birth rate wins, there's a finite chance you'll go extinct, but it happens only at the very beginning of the process, because since the population is growing exponentially rapidly, if you don't go extinct right away, you'll never go extinct. So there's a small probability, which we can compute, and actually I won't compute it now, but I leave it as an exercise for the student. You can compute the extinction probability for lambda bigger than mu. For lambda less than mu, obviously you go extinct, there's no chance of living. And so the only interesting case is when lambda is equal to mu. So we want to look at the extinction probability. So the extinction probability is just P0. That's the definition of P0. It's the extinction probability. And so, but the problem is that this extinction probability is 0 over 0, so we've got to do a limiting process when lambda goes to mu. So for lambda equals, so let's consider, so let's suppose that lambda, I want to set it, I want to make it close to 0. So lambda minus, so suppose that lambda, and now let me just refer to what I wrote here. So let me assume here, let me assume that lambda over mu is equal to 1 plus delta, with delta going to 0. Let's try that and see what happens. You can ask me too, but if you're happy. Okay. So in this case, lambda minus mu is equal to mu delta. So what is our P0? Maybe I can just put it over here. So, pardon me? Yeah, but I'm going to be interested, I'm going to send delta going to 0. But yes, we can approach it from either side. But let's, so anyways, so then here, e to the lambda minus mu t is equal to e to the mu t delta, which is roughly equal to, when delta goes to 0, 1 minus delta. I want to put the delta to the right so it doesn't, so it's mu t delta. Okay. So on the top, plus. Thank you. So on the top, we have mu t delta, And on the bottom, we have lambda over mu, which is 1 plus delta. And then we have epsilon, which is 1 plus mu t delta, 1 plus mu t delta, and then minus 1. And now we send delta going to 0, and allow me to erase these two things. And so what this goes over to, when delta goes to 0, so the 1 is canceled by this guy here, and then I have delta and mu t delta, and then I send delta, and then it's a common factor everywhere. And now, when delta goes to 0, that means that mu is equal to 1, and so we get just t divided by 1 plus t. So that's the extinction probability. T divided by 1 plus t. So as t goes to infinity, the extinction probability goes to 1. The population certainly goes extinct. So we're living on the edge of catastrophe. If we have a birth-death system with equal birth and equal death rate, the system is certainly sure to go extinct. And as a corollary to this, that means that the survival probability, which is 1 minus the extinction probability, so S, survival probability, is equal to 1 minus P naught, and so this is equal to 1 divided by 1 plus T. So what's amusing about this result is that if I now think about the good old random walk, so let's recall the random walk. A random walk, or continuum diffusion, it turns out that S of t, so if I imagine starting with a single particle at distance, well, there's only one particle in the random walk, so I start with a particle at distance 1 away from the origin, does a random walk, and I ask, what is the survival probability? Well, that survival probability is erf of, say it starts at distance x away divided by 4 dt. And this asymptotically scales as 1 over t to the 1/2. So for the random walk, it's actually more likely to survive than for this birth-death process. You had a question? Yes. Yeah, because, we were, well, I guess I already erased it, but we're interested in the limit mu minus lambda going to 1, both going to 1. And so, when I take delta equals 0, that's the same as taking mu equals 1. Okay. So this is another rich example, and it's kind of like the simplest example of a population dynamics process, but it's a very useful one because it's very rich in its phenomenology, and it has lots of amusing questions that you can ask about it as well. Lots of amusing generalizations. Okay. Any questions before I go on? All right. So the last topic that I want to present today is the role of large or extremal fluctuations in some kind of population biology system. So I want to look now at extremal fluctuations. So what do I mean by this? Let's consider some kind of a birth-death process, some kind of a stochastic process. And I guess Uwe is going to talk about some of this tomorrow in the spatial setting. But let's imagine we have the following process, that A goes to 2A, and also 2A goes to nothing. So bacteria give birth, but each bacteria hates its brother or hates its sister. And so when two bacteria meet, they kill each other. And then I want to ask, well, what happens in this system? What is the final state of the system? So once again, we can write down a rate equation for the number of individuals. And the rate equation might look something like this. N dot is equal to n minus n squared. This is a linear birth process. The rate at which people are born is proportional to the number of individuals. The rate at which people kill each other off is you need 2 to tango, and when 2 tango, they kill each other off. So it should be proportional to the square of the density. I can write this as n times 1 minus n. So if I plot as a function of n dot, so this is an upside down parabola, and so it means that when n is in this range, n dot is positive, and so you're drawn to this fixed point. If you're out here beyond n equals 1, then n, I mean, this curve goes negative, and so you're drawn to a stable fixed point here. The fixed point at 0 is unstable. So as soon as you have just one individual, you are driven by the dynamics to go to the state n equals 1. So what do you want me to repeat? Repeat how I justified it? Yeah, so there is a term here where, you know, you have each particle gives birth at some rate. Let's call it rate 1. And so the rate of growth is proportional to the number. But then, on the other hand, if you have two particles and they meet, there's a loss of particles. And what is the rate at which two particles meet? If I think of like a mean field situation, or everybody's on a single lattice site, and just how many ways can people interact? So, you know, there's, say, 50 people in this room. How many different ways can I have a battle, a fight to the death with somebody? I pick myself, so that's n, 1 out of n people, and I pick somebody else, n squared, and we're going to go outside and fight to the death. Yeah. So that's what it looks like. So it tells you then that if I have this kind of reaction process, the number here is the equilibrium number density. But in a stochastic system where I have discrete particles, this picture is dead wrong. Everything about it is wrong. And the reason why is if by some bad luck, you know, we just, before any of us decides to give birth, we all pair off and kill each other, then there's nobody left in the room to give birth, and we're dead. So once you're extinct, you're extinct. So in a stochastic system, the sense of the fixed points is reversed. This will be the stable fixed point in the stochastic system. This will be the unstable fixed point. And so what I want to do now is examine how long does it take to reach extinction first of all, examine what is the probability of reaching extinction and how long it takes to reach extinction. So that's the basic goal. So, so now let's think of, what am I going to call this? Yeah, so again, let's suppose there's a birth rate, lambda sub n, which will be some arbitrary function of n. And let's suppose there's a death rate, u sub n. And I want to engineer the system so that for small n, birth wins out over death, which is what is happening here. Here, birth is winning out over death, and so the system is going to larger n. But for beyond like an equilibrium value, death wins out over birth. So I'm not going to use this now, but for later reference, let us take lambda n equals to the total number of particles in the system. But let's take the death rate equals to n squared divided by capital N. So my units are a little bit messed up here, but the point is that I chose it in this way so that this fixed point is that little n equals big N. So really, you know, I should have written here maybe n over big N. So big N would be the equilibrium number of particles in the system. So you see that when n, little n is less than big N, so lambda n is bigger than mu n, for n less than big N, but lambda n is less than mu n, for little n bigger than capital N. And so what I want to do now is, for this stochastic process, so I have here is 0, 1, 2, 3, and I have my lambda sub n here, my mu sub n here. Well, it will be n equals 3 in this particular case. But I want to now compute the extinction probability. So the extinction probability. Let me define this thing. If I start with a system with n particles in the system, so E sub n, so extinction probability starting from n. Let's calculate that extinction probability. Now, in fact, this is in disguise a first passage process. And so, again, I don't know how much you had last week, so I'm going to write down what's called a backward Kolmogorov equation for this extinction probability. And if you've seen it before, tell me. And if you haven't seen it before, tell me. And I'll know how much I have to explain about it. So if we define E sub n as the extinction probability starting from n particles, well, the way that one solves this, like in a very simple and direct way, is that, well, let's run the stochastic process one step. And after a single step, so maybe I should have written here, you know, let's put lots of sites here. So this is like n plus 1, n minus 1. So I start at site n. Then after one step, I'm with a probability lambda divided by the sum of the rates, I'll end up here. And then the process starts all over again at this point. And with the probability mu sub n divided by the sum of the rates, it'll end up here. The process starts all over again as well. So let me define, just to make life simpler, let me define P sub n is equal to lambda sub n divided by lambda n plus mu n. Q sub n is equal to mu sub n, lambda n plus mu sub n. So this is the right hopping probability. Right hop probability. And this is the left hop probability. And so what I would say is that E sub n satisfies the following recursion formula. With a probability P sub n, I hop to the right. And when I hop to the right, I just have the same process, but starting at site n plus 1. So the extinction probability from site n is, well, after one step, I might have hopped to the right, and then I have the extinction probability or the extinction process starting from site n plus 1. Or I could have started at site n with the probability q sub n. I hopped to the left, so plus q sub n, en minus 1. Does this look familiar? Did you talk about this last? No, you didn't. Okay. So again, then let me attempt to, again, justify this a little bit more, but it's just that, you know, we start at site n, and so the probability, so that's where we want to compute the extinction probability starting from here. And so how do we compute that extinction probability? What we need to do is we have to sum up over all possible stochastic processes that end at the origin. But when we sum up over all stochastic processes, we can decompose any stochastic process into what happens after one step and the rest of the process. So with the probability P sub n, I have this process. So this is now at n plus 1. For the probability Q sub n, I start at n minus 1. And so the probability of extinction from here is just Pn times the extinction probability from here times plus Qn times the extinction probability from here. So that's what this equation is. So it's a very simple equation, but very powerful because we now have a direct equation that tells us what the extinction probability is. Now, to solve this equation, this is kind of like if you were taking a basic graduate course in stochastic processes, this would be like stochastic processes 501. And so the way that one solves this is you see it kind of looks like a second order equation, but you can make it into a first order equation by just bringing this over to the right-hand side. So let me write this as 0 is equal to P sub n, En plus 1 minus En, minus Q sub n, En minus En minus 1. So I've turned it into like a first order recursion for the difference. And so now let me call Fn, let's call it En plus 1 minus En. So this is just definition. And so finally we have that 0 is equal to Pn Fn minus Qn Fn minus 1. Or finally, Fn is equal to Qn over Pn Fn minus 1. And I can write this as now mu n over lambda n Fn minus 1. Now this looks simple to solve. Even I can solve this recursion formula. So Fn is equal to, and now the tricky part here is that you end up with like sort of products and sums, and to avoid writing a lot of glop, let me define this ratio as Rn. So here I have Rn minus 1 all the way down to R1, and then I have F0. But F0, if I go back to the definition, is E1 minus E0. E1, so that's the extinction probability starting from site 1, minus the extinction probability starting from site 0. But if I start at site 0, by definition, I'm already extinct. So the probability of being extinct starting from site 0 is equal to 1. So this is R minus 1. Let me define, and again, to avoid writing a lot of glop, let me define this thing to be capital Rn, E1 minus 1. So this is Fn. But now Fn is nothing more than the first difference of En. So all I have to do is sum this equation to get the solution for En. So what I have then is that, so what I'll do now is I just sum, j equals 1 to n of fj. Well, this is nothing more than En plus 1 minus E1. And so this is equal to the summation Rj n j equals 1 up to n of E1 minus 1. So finally, I have the following equation. En plus 1 is equal to E1 plus the summation j equals 1 to n Rj E1 minus 1. Now comes a very simple thing that gives us the answer, which is that these extinction probabilities are probabilities. They better be less than 1. This R, capital R, was a product of little r's. And notice that if birth wins out over death, then this would be less than 1. But if death wins out over birth, these are bigger than 1. And I'm specifically considering the situation where for large n, death wins out over birth. So for large n, each little r sub n, each one of these guys, is bigger than 1. And so the product of these things is even bigger than 1. And the sum of all these things is blowing up. So the point is that this is going to infinity as n goes to infinity. In order to not have probabilities which are bigger than 1, the only way that that can happen is that enforces that E1 better be equal to 1. So that means we have 0 multiplying infinity and we don't get a divergence. But if E1 equals 1, then this is 0, and then we have En plus 1 equals E1, which is 1, which means all extinction probabilities are equal to 1. So this is a very, this is a standard calculation stochastic processes, and it shows that general one-dimensional random walk processes with arbitrary hopping rates are in general recurrent, no matter what kind of hopping rates they are, as long as the hopping rates satisfy this condition that this sum here goes to infinity as n goes to infinity. And that encompasses any kind of isotropic process or any kind of process which is biased towards the left. Okay, so we now know the system goes extinct. The last part of this is how long does it take for our system to go extinct? What is a natural time scale that describes the system? You see that the only time scale that you can imagine in the problem, the only scale in the problem is n. And so how does the lifetime depend on n? How does this extinction time depend on n? And before I tell you what the answer is or derive what the answer is, let me give you just a little sort of tutorial about like what you might expect for generic types of hopping processes. So let's suppose, just for the sake of argument, that we have, again, so here is my n space. Here is capital N. We have a bias to the right here, and we have a bias to the left here. So let's call this bias velocity V, which is going to the right. And, it doesn't matter what this is actually, because in some sense, this would be like a potential minimum. You'd be driven to the potential minimum, and you're trying to go like upwind to get to extinction, and you want to ask how long does it take to get to extinction. So let me call T sub n be the extinction time. So generically, it has the following behaviors as a function of this bias velocity V. If the velocity V was negative, which meant that you have to go downstream to get there, then the extinction time is just nothing more than n divided by V. So this would be for V less than 0. Right? It's just you're following a bias, you're convecting to the origin. If the velocity was 0, then you just have a random walk process, in which case we know that the extinction time would be scaling like n squared divided by a diffusion coefficient. So this would be for v equals 0. If you want to try and surmount, what is v? V is a biased velocity. Yeah. So this is just, you're thinking of some kind of a random walk-like process with a constant bias either to the right or to the left. And finally, it scales like e to the v n over d for v positive. So in order to, go against the wind to get to extinction, the time is exponentially long. So it should come as no surprise then that for this stochastic process we're going to be discussing here, where for small n, birth wins out over death, so you're pushing the system to the right. So to get to extinction is going to actually scale exponentially long in n. And that turns out to be the answer. And that's what I'm going to attempt to derive in 6 minutes and 40 seconds. Okay. So in the same spirit as this backward Kolmogorov equation for the extinction probability, we can define a backward Kolmogorov equation for the extinction time. So let me now call T sub n will be the extinction time starting from n. And in exactly the same spirit as I wrote over here, we can write the same kind of sort of recursion formula, which is if I start at n, with a probability, I can't read my writing. This was backwards. Oh no, this is correct. I see. It's just, I did on the left, I did hopping to the right, and the right, I did hopping to the left. So everything is correct here. Okay. So anyways, so with a probability p sub n, you go to the right. And so if it takes a time t sub n to go from here, so with a probability of p sub n, it takes a time t sub n plus 1 from here, but you wasted a time delta t in making the step from here to here. Similarly, you could have hopped to the left, and then you have, with the probability of q sub n, you have the time starting from here, but you have to add the time that you wasted in making the single step. So the recursion formula is t sub n is equal to p sub n Tn plus 1 plus Qn Tn minus 1, but then you have to include the time that you wasted in taking the single step. So let's call the time you waste little delta Tn, because little delta Tn depends on where you are, because the rates are n-dependent, and the time you take for a single step will be 1 over the sum of the rates. So we have to solve this recursion formula, and I guess I'm not going to do it in 4.5 minutes, but let me just say that the same techniques that I applied here, we can apply over here. The only difference is that in the case of the extinction probability, we ultimately got to a homogeneous recursion formula. Here we'll get to an inhomogeneous recursion formula, so you've got to do a little bit more rigmarole, but let me start and let's see what happens. So first of all, delta Tn, so that's equal to 1 over the rate, inverse of the rate, the inverse of the total rate. So let's write this as total rate inverse. So that's equal to 1 over mu n plus lambda n. Oh, it's flashing red on me. My watch has 3:56, so I'm still going to go on for 3 more minutes. Okay, so I'm going to do the same stunt as I did over here, which I'll write this as 0 is equal to Pn Tn plus 1 minus Tn minus Qn Tn minus 1 minus Tn plus delta Tn. So let me write this now explicitly. So I'll write this as 1 over lambda n plus mu n. I'm going to write one more equation, which is, so you see that it looks like a second order equation that I'm trying to turn into a first order equation. And let me define capital Un. So this is definition now. And so I'm going to define this thing to be Tn minus Tn plus 1. And you might say, like, why did I change kind of the sense compared to here? And it's just because this is in my book this way, so it's just so I can remember what's in my book. So I did it that way. Anyways, so now we have 0 is equal to Pn, Pn, so it's minus Pn Un plus Qn Un minus 1 plus 1 over lambda n plus mu n. Now, remember what P is. P was equal to lambda n divided by lambda plus mu, so I can get rid of the lambda plus mu and write this more simply as minus lambda sub n un plus mu n un minus 1 plus 1. So I'm almost done with what I'm going to do today. So un is equal to 1 over lambda n plus mu over lambda, mu n lambda n, mu n minus 1. Capital U n minus 1. So notice that it looks very similar to what I had over here. I had here Fn was Q over P, Fn minus 1. Here I have Un is Q over, mu over lambda is the same as Q over P, so it's Q over P, Un minus 1, but with an inhomogeneous term. And how do you solve an inhomogeneous equation? By the integrating factor. In differential equations, you're all familiar with it, even though you might not think you're familiar with it, you are. But with discrete formulas, it's a little bit more, less familiar perhaps, but it's the same technique. You just solve it with an integrating factor. And so I've run out of time here, and so I'll leave you in suspense. But suffice it to say that by introducing an integrating factor, the same kind of rigmarole, everything works exactly the same way. And in fact, I think what I'm going to do is I'll just write down the answer because I think that there's sort of no point next time to just start in the middle of this derivation and pick it up from here. But so hopefully I want to take you out of suspense. So at the end of the day, for this, okay, let me write down the answer and then I'll do it for the specific case of the rates. If I can find where it is. So one last thing to say about this is that because the bias is driving you to the right, so no matter where you start here, the typical thing is that you fall into this potential well, and then you attempt to get out of the potential well, and at some point you have this unlucky fluctuation that kills the population. So it turns out that algebraically it's easiest to write down the solution for one single particle. What is the extinction time starting with a single particle? Because the single particle will typically go into the potential well, and then you have to escape. And it turns out algebraically the solution for T1 is the simplest, and so the solution is the following thing. T1 is equal to summation from n equals 1 to infinity of 1 over lambda sub n r sub n. That's the solution. For capital R was what we had from over here. And in particular, if lambda sub n was equal to n and mu sub n was equal to n squared over big N, this thing goes over into summation n equals 1 to infinity of the following thing. It's 1 over n to the n over n factorial. And last thing, I'm now over by 90 seconds. How does this asymptotically scale? And because of the 1 over n, you might not know the answer, but let me ask, how does this scale asymptotically? It's exponential, e to the n. And in fact, the way that you would get this is you would write the sum as an integral, do it by the Laplace method, and then you'd find that it's exactly e to the n. So what you do is you would expand this, and it's a Gaussian about the maximum value. Because there's this extra prefactor, all this does is you can evaluate this at the maximum value, which is 1 over n. And so this asymptotically scales like e to the n over n. So I apologize that my time management was a little bit off, and so I didn't show you all the details here. But it's straightforward and a little bit ugly, and in fact, it's almost like I dread doing it on the blackboard because the chance of me making a mistake is 1. And so I got myself out of that one. But it's in my, I guess I should say that everything that I presented so far in these lectures exists in my graduate text, The Kinetic View of Statistical Physics. I'm afraid to say this, like to self-advertise, but everything can be found there. So I'm done for today, and my last lecture tomorrow morning will be on the use of master equation approach to understand the statistics of complex networks. Well, the survival probability decays exponentially. So the thing is that there's this characteristic time scale, that goes as e to the n. And the survival probability is e to the minus t over tau, where tau is going like e to the n. Well, this is just generically, if I have any kind of a process where there is a stable fixed point at a non-zero value of n, and an unstable fixed point at 0, generically, the survival probability decays exponentially in time, and the characteristic time scale is given, you have to calculate for each specific process, but typically scales exponentially in n. When you say it's only at 0, what do you mean? No, this is A going to 2A. No, but A plus, that's 2A going to 2A. That's nothing's happening. Okay? Well, so again, in the context of this picture, in details don't, yeah, it doesn't really matter. All that really, the only point is that if you had like some kind of higher order process near the origin, but then something like this, you would still end up with the same feature that, the lifetime would scale exponentially in the size of the system. So, the details of the reaction don't matter. It's just the fact that you have one fixed point at a non-zero value of n that's stable in the mean field, but unstable in the stochastic process, and another fixed point at the origin, which is unstable in the mean field, but stable in the stochastic process. And generically, for any kind of reaction process with this structure, you will have the same kind of feature, that there's an extreme of fluctuation that dominates. And I know that, like in field theories, this is what's called an instanton, and there's all kinds of techniques from that allow you to calculate in detail for many different types of reaction processes. So this is the extinction probability starting from site n. So I'm starting a distance n away, and I'm asking, will I walk over the cliff or not? Eventually. So there's no time associated with this because I'm asking for the eventual extinction probability. I wait forever, starting at site n. If the cliff is over there, will I, by bad luck, walk over the cliff? That's right. So, there's the cliff, and here I am. I'm a drunkard. I don't know what I'm doing. And so I could go over here. I move one step further away from extinction. Or I could have gone over here, and I'm one step closer to extinction. And so I ask, what is the probability that it go extinct starting from here? Well, it's the same as the probability of making a step left and going extinct from there, or a step right and going extinct from there. That's the meaning of this equation.